Hello everyone! In this lecture, we will learn how delete operation works in AVL tree. As an overview, we will see 4 rotation cases for delete operation in AVL tree, such as left-left case, which requires right rotation, right-right case that requires left rotation, left-right case, left rotation and then right rotation, and right-left case, which you will be doing your own right rotation and then left rotation. From previous lectures, we already know how rotations are performed depending on the cases. In this given example, we try to delete a node which will further require us to make rotation to balance our AVL tree. So let's go on and try to delete node with a key value of 40 to see how delete operation works in AVL tree. We have 2 input arguments. As we know from the previous lectures, we search given key value by starting from the root node and the key value that we aim to delete. So in this case, we have root as first input argument and key value of 40 as the second. We skip the first if statement as we already have a structured AVL tree given in the example. So at the next 2 if statements, we check whether the key value that we want to delete is located at the right subtree or at the left subtree of our AVL tree. In our case, we know that 40 is located at the right subtree of our root node. So we call our recursion here and pass the values as the root.right and the key value that we want to delete from our AVL tree. We already know that result, which will be returned from incoming recursive call, will be the result of this recursive call's root.right. So now we can store the values in our method call and execute our new recursive call. This time, we take root.right as our new input argument and the same value that we want to delete. Our root is not null since it has key value of 40 stored in it, so again, we skip the first if statement. We know that next 2 if statements will also be skipped as we have the value which is equal to itself, so 40 is neither bigger nor smaller than 40. At the next block of code from line number 12 until line number 35, we basically do check if not to be deleted has children and take the required actions so that we do not break the formation of our AVL tree. So again, I want to take your attention that here we are not doing the actual rotations, but instead only keeping the structure of our AVL tree in valid form after deletion of a node. So let's see if not to be deleted has children. Well, in this case, we do not have any children, so this means that first if statement will be executed. Then we create a temporary node that will be used in the reformation process of our AVL tree. From line number 15 to line number 18, we check the case where one of the children is null for our incoming pointer after the node with value of 40 is deleted. So in this case, first if statement at line number 15 will be executed since temp and root.left are both null. Then we say temp value takes the same value as root.right, which is null. Here, I want to indicate that we actually do not have any nodes that are pointing at our temporary value. But for the sake of understanding, I basically use some pointers that later on will eventually be invisible since temp is a local variable. As we have executed our if statement, we skip the else statement and check the next if statement where we basically do the actual deletion in our AVL tree. So at the next if statement, we know that temp is null, so it will take the value of root and root will switch to null. We have executed 2 if statements for this and the parent, so we skip the other 2 else statements and get to the next if statement where we return root with the value of null for the previous method calls root.right. So in the previous method call, we have left at line number 8, which now is this method call. In this method call, we have root of 18 and root.right now pointing at null. It is pointing at null now because the result coming from just executed recursive call was null. At this method call, we have executed one else if statement, so until line number 35, we basically skip the next incoming statements since they are the children of the line number 10's else statement. So before we continue, you can see that the actual deletion is complete. But however, we now have to make reformation of our AVL tree since it breaks the AVL tree balancing factor definition and is not a valid AVL tree at this current state. Okay, so let's continue and see how the reformation of AVL tree is performed in delete operation. Next, at line number 35, we know that root is not null. We skip and do the recalculation of the heights as we might have a different height for our root node since a node has been deleted previously. Well, in this case, nothing has changed at the height because it still has the furthest descendant node connected with upmost two edges. But something has changed at the balance factor since now root.right will be returning -1 instead of 0. This means balance factor at line number 40 will return 1 minus -1 and the result will be +2. Well, as we remember from previous lectures, balance factor for a valid AVL tree could only be -1, 0 or +1. If the balance factor is 2, which is our case now, this means left subtree is more in weight than the right subtree and the balancing is required. There are multiple ways we can determine the case of rotation that we have in our unbalanced AVL tree. At the upcoming slides, I will show another way of how we can determine the case of a rotation to be performed. But for now, let's do the way we see in this code example. We know that we have balance factor of +2, and the rotation case can be determined by knowing the actual value that is returned from the balance factor method of the child node. If child node would return balance factor as a negative value, which will be smaller than 0, we would know that there is not a node with a key value located at the left pointer of our root node. That would also mean that we need to perform left-right rotation. But in this case, our get balance will return 0 as a value from the child node of our root node, which means there is a value at the left pointer of our root node. This also means that our AVL tree requires a right rotation. So next, let's see how right rotation is performed. Again, same as we have performed at the previous lecture, we pass the root node as our y value, x is equal to y.left, and 3,2 is equal to x.right. Y becomes as x.right, 3,2 goes to the y.left. Next, we update the heights of relocated nodes and return our head node, which is x. From the method call, we return the same outcome from executed rotation and finish the balancing. At the next example, we will satisfy the condition of right-right case at delete operation in AVL tree. At this example, we delete node with a key value of 7. At the first if statement, we know that our root is not null, so we skip it and determine with the next statements the location of our key value that we want to delete in our AVL tree. It is located at left subtree, so we execute our recursive method once again and store the values in our method call for better understanding. Our new root is now 7, which is the key value that we want to delete. So, as you remember, first 3 statements will be skipped now, as we have the value that is equal to itself. At the else statement, again, we delete the value and do necessary adjustments if needed, in case that the node to be deleted has at least one child or no children at all. Same as previous one, no children. Here anyways, I want you to go on and populate your AVL tree using insertion method that we have implemented at the previous lecture, and try to delete a node that have 2 children nodes to see how rearrangement is performed by step debugging your deletion method at the required lines. If you did this, or you will do, you may notice that AVL tree will not need a rotation, as the rearrangement after deletion will not exceed the defined balance factor value. This said, we continue with the current state of our AVL tree. We create a temporary value, which is null, and exchange it with a root node. And finally, we return our null root as a new left pointer for the previous method calls root node. Next, we know that the deleted node wasn't the only node in our AVL tree, so we recalculate the heights. Heights in this current state will not change, but the balance factor will, because now left pointer of our root node is null. So -1 minus +1 is equal to -2, which is exceeding the defined balance factor values of AVL tree. If balance factor is -2, this means the right subtree is higher in weight than the left subtree. We have two rotation cases to be performed here. It will whether be right-right case or right-left case. So same as the previous one, we can basically check the balance factor of the right child of our root to determine which case does our unbalancing fits. Here, first two if statements will be skipped since we have balance factor of -2. We know that our case cannot be right-left case because then the right child of the root's right would return -1 and 0 minus -1 would return +1, which would mean that we needed to execute line number 53 instead of 50. But however, root's right child has a key value and is not a null. So from height it will return 0, because 0 minus 0 will return 0, which means in this case line number 50 will be executed. So this means we have right case which requires left rotation. This time we pass our root as x parameter and y as x.right. T2 becomes as y.left and we perform rotation. Y.left is x and x.right is T2. We update the heights of relocated nodes and return our head node of y. We exit the rotation method, we return again the reformated nodes and finish the execution. At this example, we will satisfy the left-right case and finish our slides, leaving you the last case of right-left case, which you may try yourself and debug to see the reaction of the implemented algorithm. To be able to trigger the unbalancing factor for the left-right case, we need to go on and delete the node with the key value of 51. So I will slowly proceed on the code as we have already did the same operation twice at the previous slides. So here is how node with key value of 51 is deleted. In line number 40, we update the height of root after deletion and check the balance factor. In line number 38, we update the height of root after deletion and check the balance factor. Balance factor from the given method will be returned as +2. Now, we need to determine which rotation case does our balancing fits to form a valid AVL tree by performing specific rotation. The way that we determine the case for rotations would work perfectly fine with the given implementation. But just to show you abstractness and as a proof that any logical operation that fits to determine the rotation case would also work fine to rotate our AVL tree. So let's move on and change the if statement expression a little bit and think of how simpler it could be done to determine rotation case of our AVL tree. Well, instead of checking balance factor of the child node, we basically can check if root's connected pointers such as left.left or right.right has key value with a node at those addresses. As you can see from changed example, we are checking if root's left.left pointer has a key value with a node. So it doesn't, and this way we basically know that our case corresponds to left and right case which requires left and right rotation. So first, we do the left rotation with root's left pointer. So it becomes x argument. Y is assigned to x.right and t2 to y.left. At the rotation part, y.left becomes x and x.right becomes t2. We update the heights of the relocated nodes and return our y-hat as new root.left. Next, we do right rotation. This time, root takes the y argument, x becomes y.left, t2 becomes x.right, and we perform rotation. We update the heights of relocated nodes and return our head node of x. So here, as a reminder, I highly recommend you to try the last rotation case, which is right-left case, using the implemented algorithms. But regardless, I assume you now have better understanding on how delete operation and overall how AVL tree works in data structures. I hope you enjoyed this lecture. Hope to see you in the next lecture.